Have you ever tried to fix a fluctuating problem in your life? Like, maybe your weight is bouncing around, or your monthly grocery budget, or even...
Or a team's performance at work, right? Like when
Huh.
they're just super erratic.
Yes, exactly.
Yeah,
And you try to fix it, you constantly tinker with it, only to realize your tinkering actually made the problem much, much worse.
because you tweak one thing and then something else breaks.
Right? You overcompensate, and suddenly you are completely lost in the weeds. Well, welcome to today's deep dive. Today, we are decoding the hidden mathematical language of processes using excerpts from an introduction to statistical quality control.
It's a fascinating subject.
It really is. Whether you are manufacturing aerospace components, processing mortgage applications, or, just trying to optimize your morning routine, we are going to teach you how to definitively separate random, meaningless noise from a system that is actually broken.
And that tinkering you just mentioned, that's exactly why understanding this mathematical language is so crucial, because every single system in the universe has natural variability built into it.
Yeah, nothing is perfectly static.
Right. Your weight fluctuates day to day based on water retention. Your commute time changes by a few minutes depending on traffic lights. Even a heavy-duty industrial machine cuts metal a microscopic fraction of a millimeter differently each time the blade comes down.
Right, it's just physics.
Exactly. Reacting to that natural, inherent variability without actually understanding it is a recipe for absolute disaster. In the engineering world, they call this over-control.
Over-control.
Yeah, you end up chasing ghosts, basically, adjusting dials that don't need to be adjusted, and you just inject more chaos into the system than you started with. So to stop doing that, we have to look really closely at the math behind the process.
And to stop ourselves from this, unnecessary tinkering, we first have to figure out what the system is actually doing on a baseline level. We have to measure it.
You can't fix what you don't measure.
Exactly. But measuring just one aspect of a system gives you a dangerously incomplete picture. It requires this two-pronged attack.
Yeah, the mean and the variability.
Right. When we're tracking a variable, which is simply a quality characteristic measured on a numerical scale, like length or
Yep.
temperature or volume,
Yeah.
we have to track both where the system is aiming and how widely it's scattering its shots.
That's a great way to put it.
We do this by monitoring the mean, using what's called an X-bar chart, and simultaneously monitoring the variability, using an R chart for range or an S chart for standard deviation.
And that two-pronged attack is completely non-negotiable. I mean, the X-bar chart tracks the average. Like, are we, generally speaking, hitting the target?
Right.
But the R chart, or the S chart, that tracks the spread of the data. How far are the individual points bouncing around away from that central average?
So the R chart is just the range, right?
Yeah. The R chart or range chart just looks at the absolute highest point and the absolute lowest point in a sample and measures the distance between them.
Okay.
But an S chart for standard deviation is a bit more rigorous.
Yeah.
It tracks the average distance of every single point from the center line.
Which gives you a much better picture of the overall spread, rather than just looking at the extreme outliers.
Precisely. You must have both the mean and the spread. Because think about it, if the mean shifts, your average output is wrong. But if the variability shifts, your output is completely unpredictable, even if your average happens to be perfectly on target.
Right. It's like driving a car on a highway. The X-bar chart, tracking the mean, measures whether you are generally centered in your lane.
I love this analogy.
But the R chart, tracking the variability, measures how wildly you're swerving back and forth within that lane.
Right, the swerve.
You can be perfectly centered on average, like swerving 2 feet to the left, then 2 feet to the right, so it averages out to dead center. But if you're swerving that wildly, you are still going to crash into a guardrail.
You absolutely will, which highlights a fundamental rule of process control, which is you literally cannot fix a mean problem like drifting out of your lane with a variability solution.
Like tightening the steering column.
Exactly, and vice versa. If your process variability is out of control, the mathematical limits on your X-bar chart lose all meaning. The baseline is simply too chaotic.
So you have to stabilize the swerving before you can accurately judge if you're actually centered.
Exactly. You fix the spread before you fix the center.
So if measuring the swerve is that critical, how do we know what a normal swerve is for our specific car? Like, how do we build that initial baseline?
Well, this usually happens in two phases. Phase I is all about looking backward. We take 20 to 25 preliminary samples, just historical data, to calculate trial control limits.
And then phase 2?
Phase 2 is when we lock those limits in to monitor future production. But during phase 1, the goal is to actively hunt for what they call assignable causes.
Okay, what's an assignable cost?
It's when a historical data point is wildly outside the norm because we know something specific happened, like a power surge happened or a new operator pushed the wrong button. If we know why it happened, we throw that specific data point out.
Got it. By eliminating the data points where a known special circumstance occurred, we mathematically strip away the weird anomalies.
Exactly. The goal is to find the true, natural, unbothered state of the underlying process. You just recalculate those trial limits without the bad data over and over until a highly stable pattern emerges.
Well, wait, hold on. I have to push back on this.
Okay, go for it.
If we're just establishing a baseline from historical data, what if the historical data is just a record of a really terrible, completely broken month?
Ah, yes.
Like if a factory machine has been spewing out defective parts for 4 weeks and we use that month's data to build our charts, aren't we just mathematically standardizing a bad process?
This is the exact trap so many managers fall into. It really is. You have to separate the concept of control from the concept of capability.
Okay, break that down.
When we revise those trial limits in phase I to find a stable pattern, we are applying intense mathematical rigor simply to find the natural rhythm of the machine. It's not about standardizing good quality yet.
It's about standardizing predictability.
Yes. We are just asking, is this process behaving the way it normally behaves without any weird outside interruptions? A completely terrible, highly defective process can be completely predictable.
That is so counterintuitive.
I know, but you absolutely must establish predictability first, because if a process isn't predictable, no targeted improvement you try to make will stick.
Okay, let's unpack this, because establishing predictability leads to a pretty brutal reality. Once we've proven our process is completely predictable and all our points are staying safely inside our calculated control limits, does that mean we are actually doing a good job?
Surprisingly, the answer might be no.
Right. And this all comes down to the critical, often misunderstood distinction between control limits and specification limits.
This is huge. Control limits are driven by the natural physical variability of the process itself. They are mathematically derived purely from the data you collected.
So it's what the physical process can do based on the laws of physics and mechanics.
Exactly. Specification limits, on the other hand, are completely externally determined. They are what management or the engineers or the customer wants the process to do.
And the textbook makes it very clear. Plotting specification limits on a control chart is completely incorrect.
It's totally wrong, because there is no mathematical or physical relationship between what the machine does and what your boss wants it to do.
So to put this in everyday terms, it's like a boss demanding a team process 100 emails an hour when the software physically takes 45 seconds to load each email.
Perfect example.
The defects aren't the team's fault. It's the physics of the software. And this brings up a formula from the source called the process capability ratio, or C.
Yeah, the C ratio.
It basically compares the width of what the customer will accept against the width of what the machine naturally produces. If your CP is less than 1, it means your process naturally takes up more than 100% of the allowed tolerance band.
And the implications of a CP less than 1 are staggering for anyone in management. It means that you can have a flawlessly operating, completely predictable, fully in control machine that is mathematically guaranteed to produce defective units.
Guaranteed.
Yeah, it is running exactly as it was perfectly designed to run. But management specifications demand something the machine's natural physics simply cannot deliver.
In that scenario, yelling at the operator to work harder or nervously tweaking the dials will accomplish absolutely nothing.
Nothing at all. You have to fundamentally redesign the process itself or just go buy a better machine.
That is such a profound shift in perspective. You stop blaming the worker and you start looking at the physics of the system.
Changes everything.
But let's say our CP ratio is great. We are inside the specification limits and our points are bouncing around nicely inside our control limits. Are we safe then?
Not necessarily.
Right, because even within the safe zone, the patterns of the data tell a dramatic story about the physical reality of the work. It's like reading the tea leaves of the math.
I like that.
So if the points are staying inside the lines, but doing it in weird ways, what are we looking for?
Well, the patterns are where the control chart transcends being a basic graph and becomes a highly sensitive diagnostic instrument. There are several specific patterns to watch for even when no single point goes out of bounds.
Like what?
For instance, a trend, which is a continuous movement of points steadily marching in one direction over time.
Okay, mechanically, why does this happen?
Think about a metal drill bit. Every single time that bit cuts a hole, It loses a microscopic layer of atoms due to friction.
Oh, sure.
Over thousands of cuts, the physical diameter of the drill bit gets microscopically smaller and smaller. The trend on the chart visualizes that slow, physical degradation of the tool before it ever produces a single bad part.
That is so cool. And another one is the stratification pattern, right? Where the points cluster unnaturally tight right around the center line. It looks great to an untrained eye, but it shows a total lack of natural variability. Mechanically, that often means the control limits were calculated incorrectly in the first place, or someone is cherry-picking the best samples.
People do that a lot, unfortunately.
But what physically causes points to wave up and down in a regular cyclic rhythm?
That brings up one of the most fascinating diagnostic moments in statistical history mentioned in our source material.
The air compressor story.
Yes. There was a cyclic pattern showing up on a chart tracking the fill volume of a metal container in a factory. The points were waving up and down in a perfect rhythm.
And they had no idea why.
Exactly. The engineers couldn't figure out what physical mechanism was causing the fill volumes to rhythmically rise and fall. Eventually, they realized the rhythm on the chart perfectly matched the on-off cycle of an air compressor located somewhere else on the filling machine.
I just love the detective work of this. This mathematical chart essentially heard an air compressor turning on and off across the factory floor just by tracking microscopic changes in the volume of the liquid.
Yep. The air compressor would kick on, draw power, or change the air pressure, slightly alter the physical force of the liquid dispenser, and the control chart caught it.
It proves the control chart isn't just an administrative compliance tool. It visualizes the invisible physical forces in your environment.
It really does. It translates environmental changes, operator fatigue, voltage fluctuations, and wear and tear into a visual language you can read.
Incredible.
And another classic pattern is the mixture pattern, where the points tend to fall out near the extreme edges of the control limits with almost nothing in the middle.
Oh, like a hollow middle. What causes that?
Mechanically, this is usually caused by overlapping distributions, but most often it's the visual footprint of overcontrol.
Back to the tinkering.
Exactly.
Mhm.
An operator nervously tweaks a dial too far to the left, realizes they overshot, and overcompensates by tweaking it too far to the right. The result is that mixture pattern.
Here's where it gets really interesting, though. So far, we've been talking about factory floors, cutting tools, and filling bottles.
Right.
It sounds strictly meant for high-speed manufacturing, where you are making 50,000 widgets an hour. But these exact same mathematical principles don't just apply to factories. They govern the service sector and desk jobs, too.
Absolutely.
Whether you are processing loans, paying invoices, or tracking your own daily habits, the math works. But how do we apply this if we aren't pulling 5 widgets off an assembly line every hour?
Well, it requires a slight adjustment to the math. When you are processing, say, mortgage applications, you aren't grabbing 5 applications at random out of a bin to measure their average cost.
Right, you do them one at a time.
You are looking at data sequentially as it happens. The sample size is 1. This requires what's known as the Schuhart control chart for individual measurement.
Right, where n equals 1.
Mhm.
But if we only have one item, how do we measure the swerve? How do we calculate the variability if there is no sample group of 5 items to calculate a range for?
By tracking the velocity of change using what's called the moving range,
Moving range, okay.
instead of comparing a group of 5 items to each other, you compare an item strictly to the one immediately before it.
Oh, I see.
Yeah. If an application takes 10 days to process and the next one takes 12 days, the moving range jump is 2. If the next one takes 11 days, the jump is 1.
And that moving range calculation estimates the instantaneous variability of the process over time without needing a batch of samples.
Exactly. It's brilliant.
And a perfect example of this from the text is a bank that tracked the average weekly costs of processing mortgage loan applications. For months, the cost was perfectly in control. The moving range was stable.
Boring, even.
Boring is good. Then, suddenly, the moving range chart caught a massive, undeniable spike at weeks 39 and 40. The mathematical jump between the weeks was just too severe. The control chart essentially waved a red flag.
And because they caught it mathematically, they looked into those specific weeks.
Right, and they realized the massive variation was caused by new, untrained underwriters entering the process or temporary workers covering for summer vacations.
It perfectly separates the systemic signal from the random noise.
It really does.
Another brilliant application from our deep dive today was a corporate finance department using these exact charts to track their accounts payable flow time.
Oh yeah, paying the bills.
Yeah, they were taking way too long to pay suppliers and missing out on lucrative prompt payment discounts. By tracking the flow time of just 5 check requests a day using statistical quality control, they isolated the systemic bottlenecks.
And what were the results?
Within 9 months, they reduced their late invoices from over 90% down to under 3%. They saved the company hundreds of thousands of dollars in realized discounts just by applying factory math to office paperwork.
I mean, the source even notes John Deere used statistical process control to test a programmable bandsaw before they even bought it.
Oh, that's smart.
They made the supplier run the machine and produce a control chart to mathematically prove the saw was physically capable of staying in control before they signed the check.
Smart procurement right there.
It just proves these tools are universally powerful. You can apply them to anything you can measure.
They are universally powerful, yes, but there is one fatal flaw that can render them completely useless, and it's a trap that is incredibly easy to fall into if you don't understand the underlying logic.
What's that?
It's the concept of rational subgrouping.
Ah, yes, the aerospace casting story. This is a great one. So, an aerospace manufacturer was making complex metal castings for jet engines. They had to measure the height of the little metal veins on the casting.
Right.
They were taking 5 veins from a single casting, grouping those 5 measurements together as their sample, and plotting them. And the charts were going absolutely wild, out-of-control signals everywhere, alarms ringing.
A total mess.
But wait, why does it matter how we group the data if all the raw numbers end up in the same spreadsheet anyway?
Because if you group the data wrong, the math lies to you. Yeah. Control charts don't just measure raw numbers, they measure the relationship between how you collected the data and the physical reality of the process. The X-bar chart monitors the variability between the different samples you take over time.
Okay, between samples.
But the standard deviation chart measures the variability within a single sample. In the aerospace example, all 5 veins in their sample were formed in the exact same wax mold on a single casting. Physically, they were created simultaneously under the exact same temperature and pressure conditions. Therefore, the variation within that sample of 5 veins was incredibly artificially tiny.
It's like trying to measure the average height of a family. If you measure 5 identical quintuplets, your within-family variation is basically 0. They are identical.
Exactly.
But if you compare those quintuplets to the entirely different family next door, the variation is huge. The factory's math got confused because it thought the identical quintuplets represented the variation of the whole neighborhood.
That is a perfect way to explain it.
The standard deviation chart, measuring within the sample, looked great because veins on the same casting are basically identical. But the real variation in the factory wasn't from vein to vein on the same part, it was from casting to casting.
Right, because their within-sample variation was so artificially tiny, it made their overall control limits impossibly narrow.
So every time a new casting came down the assembly line that was just a normal, tiny bit different from the last one, the X-bar chart triggered a massive alarm because it violated those impossibly narrow limits.
The baseline they built was an absolute illusion based on irrational grouping.
So how did they fix it?
The solution was simple but profoundly important. They stopped treating the 5 veins on one casting as a subgroup. Instead, they took the average height of all the veins on one casting and treated that average as a single individual measurement.
Oh, so they switched to the individual and moving range charts we just talked about.
Precisely. By measuring the jump from casting to casting, the process immediately came into perfect focus. The machine was actually in control the whole time. The engineers were just wearing the wrong mathematical glasses.
So what does this all mean for you listening to this right now? We've gone on quite a journey today in this deep dive.
We covered a lot of ground.
We really did. We started by realizing that to truly understand any system, you have to measure both its mean-like, are you centered in the lane, and its variability, how wildly are you swerving.
And we learned how to build a reliable baseline by throwing out the weird anomalies in phase I to find our natural predictability.
Right, because predictability must come before improvement. We also uncovered the hard truth that being perfectly predictable and in control doesn't mean you are meeting the specifications.
You have to respect the physical limits of your system rather than just yelling at the operator.
Exactly. We saw how the patterns inside the control limits can act like a diagnostic stethoscope, hearing air compressors across a room, or diagnosing the microscopic dulling of a drill bit.
And we learned that these tools apply just as beautifully to mortgage processing and paying invoices as they do to jet engine parts.
provided you rationally group your data.
Provided you rationally group your data, yes.
So you don't need a factory floor to apply this. By tracking your own variables, whether that is the number of deep work hours you get a day, your monthly grocery budget, or your team's output, you can stop overreacting to the natural built-in noise of life.
You can stop the unnecessary tinkering.
Stop the over-control and start fixing the actual underlying system. But I want to leave you with one final, slightly provocative thought, drawn directly from a subtle detail in our source material.
Oh, the psychological factor.
Yes, there's a well-documented phenomenon that sometimes simply introducing a control chart program improves the performance of the process immediately.
It's amazing.
The shift happens purely due to the motivational and psychological factors of the workers. Just knowing the process is being measured and seeing the chart on the wall changes human behavior before a single mechanical adjustment is ever made.
Just the act of observing it changes it.
Exactly. So I want you to ponder this. If measuring a system inherently changes the system, even before you apply any complex math or make any physical changes, what uncontrolled, chaotic process in your own life might instantly improve tomorrow simply by the act of you choosing to rigorously observe it?